Hopefully you can all see my screen. I'm not sure whether you can yet. Oh, here we go. There we go. That's looking better. So welcome to this class then, guys. Hopefully everybody's had a nice and relaxing week. If you haven't seen our first GCSE chemistry class, then please feel free to go back and find it. We've got one that we did last week, which should be up on our area. So if you'd like to come and watch that one, then please feel free to do that. Hopefully you've seen that the slides for today's lesson are in the link, so are in the description. So if you wanted to get hold of those slides, you could, and you could get a good follow along nice and easily. If you've got a tablet or something, then you can annotate the slides with me as we go, which is a really good idea. So I've got a couple of questions. Hello, 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 welcome, welcome. What courses will be on the new GCSE area? So it should be the main exam boards, but at the moment we're looking, and I'll talk about it a little bit more in a minute, but at the moment we're looking at just doing our tutoring for GCSE. So we'll just have our web classes at the moment, but we are going to cover the full curriculum, etc. And I'll talk a little bit more about that in a second. You've said, oh, hi, I'm in year 8, is this suitable for me? You're more than welcome to stay. You may find this a little bit above your content at the moment. If you wanted to go and watch our last week's lesson, you might feel like you can keep up with this content this week, but there might be some bits this lesson which you struggle with. So feel free to join in and you can ask questions as you go along. I'm more than happy to try and answer questions. See how you feel. This is GCSE level chemistry, so if you'd like to have a go, have a go. Lovely. So welcome those of you who have just joined. This is our second GCSE chemistry web class, our live GCSE chemistry web class. So feel free to go and have a look at our first class if you didn't manage to see it as well. That was last week. Welcome back to those of you who I think I saw here last week. So that's really nice to see people back again. That's really good. Great to see you. Well done. We'll just give it another 10 seconds or so and then we'll get started, I think. Yes, nice to see names again, recognizable names. So well done, guys. Yeah, hello again, Evan. I recognize your name, and I think Amy, I recognize your name as well. So hi, guys. Okay, shall we get started then? I think that is a good idea if everyone has got themselves sorted, if we're all ready to go. So don't forget that I'll say again, the slides and PDF is in the description. So if you want to follow along on your own tablet or something, or you want to use it at a later date, and then please feel free to grab those slides to use them. Okie dokie. So a little bit about me. Then I am the lead GCSE chemistry tutor or teacher with SnapRevise. I've got a PGCE in chemistry from Oxford University, and I've been teaching A-level chemistry now and GCSE sciences for over the last 6 years. So really enjoying teaching, really love science. I think it's by far and above my favourite subject, and chemistry is my favourite of the sciences as well, though. Of course, biology and physics are both brilliant. Chemistry is definitely my favourite. So just, I touched a little bit on this, but Callie, I think this is just to try and answer a bit of your question as well. We're hoping, or we're going to be starting up at least 4 classes a week for GCSE students in chemistry, physics and biology. We're going to cover the full curriculum. We've got our beautifully coloured, clear, simple handouts for you to use as well. We have a library of past recordings and one-to-one support. So if this is something that you guys think you might be interested in or might be useful to help you with your studies over the next couple of years, then please sign up to our mailing list. So if you follow this link, if you haven't done it already, if you follow this link, which is in the, will be in the chat as well, there you go, it's just appeared in the chat. So if you follow this link to put your email address in, you'll join our mailing list. We can keep you up to date with when it's coming live and what we have available for you and everything. And also 10 accounts are going to get the opportunity to win Snap Provides tutoring for the rest of the academic year. So it's the opportunity to get this for free, which would be amazing. So please enter your link. I'll put that again at the end of the lesson, just in case you miss it. That's for those of you that haven't, who've only just joined us. Please pop your email address in on that link. I'll put it again at the end. Right, so yes, there will be a lucky draw. Then 10 people will get the opportunity to win a free account, which is amazing. And I agree, science is best. Yeah, we can just say science is best. Okay, so this lesson, we are going to, hopefully by the end of it, we will be able to understand mass number, atomic number, and how to calculate the number of subatomic particles in an atom. So we looked at subatomic particles last week, in our class last week. So this week, we're going to use that information to look at understanding mass number, atomic number, and how to calculate them. We're also going to understand the difference between an atom and an isotope, how they are ever so slightly different when we're talking about an atom, what are we describing, and when we're describing an isotope, what are we describing? And then we're also going to understand how to calculate the relative atomic mass for an element, which is a little bit of maths that we need to do towards the end. Over the course of this class, if you have any questions, please feel free to pop them in the chat. I will try and keep up with what you are saying. If I miss a question though, please put it on again, because sometimes the chat disappears and I can't see it. So please keep talking to me. If you have questions, please put them on there. If you don't understand something, please put that on there. If I make a mistake, please put that on the chat, because everybody's human. So if you spot something that I've done wrong, or you think something's a little bit off, please pop that in the chat. Welcome to those of you that have only just joined us. We are about to get started. So let's have a go then. So those of you who know what your exam board is, hopefully you do, just have a quick look over these slides, because this is specifically talking about the areas of the specification for your exam board that we're going to be looking at today. So each exam board has a different specification. Yours tells you exactly what your exam board is going to be looking for from you. So for AQA, this is what AQA is going to be looking for from you to do with our lesson. OCR, this is what they're going to be looking for you specifically to do with this lesson. And then similarly, Edexcel as well, this is what they're going to be looking for from you to do with this lesson. So let's have a look then at what we already know. So who can tell me, just remembering this is a recap of last lesson, so if you were present in our last session last week, you might be able to tell me. If not, you might already know. What can you help me to name the parts of this atom in front of us? What are the different subatomic particles we might find in an atom, and what are their names? Where are they? That sort of thing. So pop it on the chat. Let me know what you can see, what I can name on this image above. Lovely, good, really nice stuff there, guys. So we've got electrons on this outer shell, or in the outer shells. These are our electrons. I've seen some people naming this as the nucleus, and we've also specifically put things in the nucleus. So I can see we've got protons in there, and then we've also got neutrons. Very nice. Well done, those of you who have put that. Very nice, very good, well done. So last week as well, last session, we said atoms have no overall electronic charge. They're not charged, they're neutral in total. Why is this? Why do they have no overall electric charge? Why are they not completely positive or completely negative? Why are they neutral? Can you pop that in the chat? Electrons are orbiting the shells. Yeah, they are. Good. But why are they neutral then? Yeah, very, very nice. We've got some really good answers here. Good. And the key point being they cancel out. Good. So we've got the same number of protons, which are positive, and electrons, which are negative. So atoms have no overall electric charge because the number of positive protons equals the number of negative electrons. Good. Oh, electrons, that's supposed to say. Electrons. Really nice, well done. So they cancel out. You've got to have an equal number of positive protons and negative electrons. Electrons are negative. I like that. Or electrons are negative with the E. Yeah, very nice. I like it. Lovely. So we've got the same number of each. Really good. So first part of this session then, we're going to be talking about specifically about mass number and atomic number. Those of you that have just joined us, we're just getting onto our new first bit of our new content, mass number and atomic number. So atomic number, what is this? What is this telling us about? What's the definition? What is an atomic number of something? And do you know what other people call the atomic number sometimes, or what it used to be called? What is the atomic number? And then what is the mass number as well? What's that describing? What's that talking about? What are the atomic number and mass number of an electron? Lovely, we've got some answers coming in already. That's great. Good. Lovely. So I'm going to be a little bit, yeah, well done, Evan, that you've got the other name as well. Brilliant. Good. So our atomic number, sometimes known as the proton number, but for you, we have to call it the atomic number. It's only older science documents that might call it the proton number. We should really call it the proton number, the atomic number. But you're exactly right. It tells us the number of protons in an atom. And this defines the element. So if you were to pick up just a random atom off the street, if you were to just pick up a random atom off the street, you would count the number of protons it had, and that would tell you what element it was. That would tell you what type of atom it was. So if it had 6 protons, it would be a carbon. If it had 1 proton, it would be a hydrogen, for example. So the number of protons defines the element. And the mass number, I think some of you said as well, also used to be, we used to use the term mass number, or I think we're talking about atomic mass or atomic weight you might be talking about. We used to use those interchangeably, but at the moment our mass number just means the number of protons and neutrons, or protons plus neutrons. Protons plus the number of neutrons. And it's anything that has any mass in a atom. And if you aren't sure, if you're ever presented with 2 numbers on your periodic table, or you can't remember which is which, or in an exam question, the mass number is always the more massive number. It's always the bigger number. And I like to use that word massive because it's got the word mass in it. The mass number is the more massive number. And it has to be, really, because the atomic number is only talking about the number of protons, whereas the mass number is the number of protons plus neutrons. So our mass number has to be bigger because it's got more, it's including more things. So the mass number of an element, of an atom, the atomic number of an atom versus the mass number of an atom, of the same atom, the mass number is always going to be bigger when you're comparing them, because the mass number includes neutrons. I guess apart from if you talk about hydrogen, because hydrogen's weird and it doesn't have any neutrons. That's looking really good though, guys. Really nice. So why then do we not include electrons in our mass number? Why have we chosen to exclude electrons? And again, this is linking back to our lesson last week. So if you need to go back and watch that, please do. Why do we not include electrons then in our mass number? Lovely, really good use of words here. Yeah, very nice, good. Oh, and Lottie's even given us an approximation to how much they, what their relative mass is. Really nice. So it is because, like you guys said, they have negligible, and this is where I can't spell negligible, That's why. Negligible. Negligible. Oh, no, I can't spell at all. Mass. There we go. Negligible mass. So they've got negligible mass. That basically means it's not noticeable, the amount of mass that they contribute to the mass of an atom compared to the mass of the atom. So we say it's negligible, and that's a really good word to use or to learn to do with this topic, because that will help your examiner to see that you know exactly what you are talking about. Really good. Yeah. So good question, Dee. So we had a discussion about this last week. There's nothing defined in your specification about what your exam boards accept or don't accept. I think if you talk about, if you can remember 1/1836, then brilliant, because that is kind of accepted as the most, I guess, accurate representation of the relative mass of an electron. But sometimes we approximate it. So sometimes we say that it's approximately 1/1840. Sometimes we say it's approximately 1/2000. So if you can remember 1/1836, that is perfect. That is very good. So then, what have we said? I think some people have said it in the chat already, but I have been choosing to keep it, to not write it down until now, because the number of electrons, how do we know how many electrons an atom has? In a number of electrons in an atom, and I'm using this keyword atom because I want to make sure that it is a neutral atom. How do we know the number of electrons? So Zari say, isn't the atomic mass the same as the number of electrons? It's not the atomic mass, it's the atomic number is the same. Good. So it's the same as the number of protons. Really good. So the number of electrons is the same as the atomic number, which tells us the number of protons. Number of protons. Now, the atomic number doesn't tell us the number of electrons. The atomic number tells us the number of protons. It just happens that in a neutrally charged atom, the number of electrons has to equal the number of protons, which is also the atomic number. And then how do we work out the number of neutrons then in an atom? How do we work out the number of neutrons? Whilst you're doing that, I've also got a question. Do you also cover A-level biology in live revision sessions? Yes, we do. There are live YouTube classes covering the science A-levels. I think it's every Sunday, but you'd have to check the timetable as to when they are. And we also have web classes. If you become a member on our SnapRevise website, then once you have an account, then you can join biology, live biology A-level classes, and chemistry and physics and maths as well. And then you have drop-in sessions with a tutor. There are live web classes, etc. as well. So we do offer that for A-level sciences as well. And there you go. There is our schedule for you as well. So you can check that out. So really good, guys. So we've just seen that the number of neutrons, it's not always the same as the number of protons. This is a common mistake, actually. It gets easier to see as you get heavier atoms. But in order to work out the number of neutrons, because our mass number is protons plus neutrons, and then we know our atomic number, if we take the atomic number away from the mass number, so we do mass number minus atomic number, that will give us the number of neutrons, because our mass number is our protons plus our neutrons, and our atomic number is just our protons. So we're saying protons plus neutrons minus the number of protons just leaves us with our neutrons left. So that's how we work out our neutrons. Really good, those of you who got that, really nice. And so just so that we are aware, electrons aren't included in the mass number because our mass number is just looking at the number of particles or subatomic particles in the nucleus. So it's only really things in the nucleus or particles in the nucleus that have any mass. So we're only really considering, the mass number is only really considering things in the nucleus. Brill. Okay, let's have a go at calculating that then. Let's have a go at calculating some of these numbers, see how we get on. So sodium, of which we've got a picture here of the electron configuration, the pattern of electrons in a sodium atom. It has a mass number of 23, and I'm going to underline the key information in my question because that is a good habit to get into, guys. So sodium has a mass number of 23. How many neutrons does an atom of sodium have? So can anybody see any bits of information we might want to use here, or how we can work this out? How can we work out how many neutrons an atom of sodium has? No, so the mass number is 23. So what is the, oh, lovely, yeah, it's looking good, guys. There are some good calculations going on here and some good answers, so really good. Well done. So I think somebody said that the atomic number 11, and you're exactly right there. We can see using this picture that the number of electrons, I'm just going to call them E's for the moment, is 11. The number of electrons is 11. E minus is. The number of electrons is 11. So how many protons? Number of protons. How many protons are there? If there are 11 electrons in a neutral atom of sodium, because it's an atom of sodium, how many protons are there? If there are 11 electrons and it's a neutral atom, there must be 11 protons. Really good, well done. So if there's 11 electrons and 11 protons, we know how many protons there are. We know that the mass number is the number of protons plus the number of neutrons, but I just want to know what the number of neutrons are. So the number of neutrons, number of neutrons is the mass number minus the number of protons, or the atomic number. We can call it the atomic number as well if you wanted, because they are the same thing, which is, as you guys said, we've got 23, been told the mass number is 23 up here at the top. So we've got 23 minus the number of protons, which we worked out as 11. So our answer has to be 12. Really good to those of you who got that straight away. That was really good. Lovely. So let's just see how everyone is feeling. And those of you who might have only just joined us, welcome. You might be a little bit far behind, but that's absolutely fine. How is everybody feeling? Let me know in the chat. Are you feeling pretty good? Number one, you feeling, oh, this is all right. I'm keeping up, but it's not perfect. Or are you super confused? I'm going to need to go through this again. Let me know in the chat. Lovely, really good. Brill, thank you for that, everybody. Brill, okie dokie. Fantastic, we will keep going then. So let's have a go at an exam question. This is an exam question from an Edexcel paper, but it's relevant to everybody because everybody could be asked to do something like this. So an atom of, have we done isotopes? Not yet, Kurt. Nope, that's coming towards the end. That's at the end of this video, or towards the end of the video. We're making sure we understand the differences or the subatomic particles and how to work out atomic number, mass number, etc. first. Yeah, but we will get there. We will get there. Okay, so an atom of copper has an atomic number of 29. Again, I'm just going to highlight this key information, and a mass number of 63. Complete the table below to show the number of protons, neutrons, and electrons in this atom of copper. Anybody want to have a go? Pop it in the chat. Can you work out what the number of protons, neutrons, and electrons in this atom of copper are? You might need to do a little bit of maths if you haven't already. Lovely. Good. We've got some answers coming in already. That's amazing. Just give everyone else another couple of seconds. Fantastic. Really good. Yeah. Well done, guys. So hopefully you've seen, if I've got atomic number of 29, this is the same as the number of protons, or this tells me the number of protons. So I know the number of protons must be 29. I also know that if it is a neutral atom, there must be the same number of protons as electrons. Oops, the same in a neutral atom. And then I can see those of you who worked out our mass number is 63, which is the number of protons plus the number of neutrons. So our number of neutrons must be 63 minus the number of protons, which in this case is 29. So those of you who can do quick maths, well done. This is 34. Really good. Well done, team. We've got lots of people doing really well at the moment, which is great. So if you managed to get all 3 correct, you would get both marks. This is worth 2 marks. If you managed to only get 1 or 2 correct, unfortunately, you only get 1 mark. So you have to get all 3 right to get that second mark. Oh, good question, Zara. So we're not talking about we're not talking about the mass of protons here. This is the electrons. This is the number of electrons. So it's like comparing, saying you've got 50 elephants and then 50 flies. We're just counting them at the moment. We're not comparing their masses at the moment. So when we're talking about showing the numbers of protons, neutrons, and electrons inside an atom, we're just counting them. We know they're there, we know they're present because they do things, they interact with things. We know that they exist in an atom, so we can still count them. They just don't, they're so tiny that they don't have any mass. That's all. Okay. Let me know if that doesn't make sense, Zara. Okay, then let's move on then to isotopes. So we're going to look first at a bit about what isotopes are, and then we're going to look at calculating some mathsy bits to do with isotopes. Please feel free to drop any questions in the chat. Welcome to those of you who've only just joined. If you wanted to, you could go and watch our previous lesson from last week. Otherwise, we're going to have a look now at some isotopes. And also, if you don't have the PDF, you can get the PDF for this lesson. It's somewhere in the chat, but it's also in our description. So if you want to get the slides and you haven't got them yet, you can grab them there. That helps you to keep up with us. You can look at it in your own time. You can make your own notes on the slides. So go for that if you would like. So isotopes then, guys, what is an isotope? What do you understand an isotope to be? Can you remember your GCSE level definition of an isotope? And we have to have memorized this definition of an isotope. You have to know which are the keywords they're looking for to make sure you get them in your answer, because this could be something you are asked in your GCSE level exams. So good, we've got a couple, which is really nice. Yeah, lovely. Good. So isotopes are, and we talk about them as being atoms of the same element. And if they are the same element, then I think, as some of you have put, they will have the same number of protons, because every element or every atom of lithium, for example, has 3 protons. Every atom of oxygen has 8 protons, etc. So the atoms of the same element must have the same number of protons, but what is my writing doing today? Different numbers of neutrons. And I've seen that some people have given examples, which is amazing. The ones that you're often seeing, hello, welcome to those of you that just joined. You might notice that you are often given chlorine as an example, because it's one that we can use quite easily in maths, when we're doing the maths questions to do with this. It's also, one that's used quite a lot in our life. So you might have met chlorine, or you might be aware of what chlorine is. So chlorine has isotopes, and these are chlorine 35 and chlorine 37. Why have we got this number? What does this number mean, 35 and 37? When we're talking about our atoms or isotopes, what is that number? Why have they given us that number? Oh, straight in there, very nice. Yeah, well done. That is a lovely definition there as well. I've just seen. Good. It's the same mass number. So it's the same. It's talking about the mass number. 35 and 37 are the mass numbers of chlorine, of these chlorine isotopes. So when you've been given a question and it says chlorine 35, you know that 35 is the mass number of chlorine. Because it's an element of chlorine, you should already, using your periodic table, be able to work out how many protons it's got, because you've been told it's chlorine. So it must have, I think it's 17, but don't quote me on it yet. You must have that many number of protons. But because it's got chlorine, you've been told it's 35, we can then work out how many neutrons it's got. Or 37, for example. It has 17. Thank you for checking for me, that's brilliant. So let's do another couple of calculations using an isotope this time. So chlorine has an atomic number of 17, there we go. So how many protons must chlorine, let's do chlorine 35 first. How many protons must chlorine 35 have? How many electrons must it therefore have? Because it's a neutral atom. And how many neutrons has it got? Have a go at doing some quick maths again. It's the very same process that we've just done. It's just they've told us what the mass number is in the name. So really good if you've had a go. Lovely. We've got lots of answers coming in, which is looking good. Brill. So we know we've been told chlorine has an atomic number of 17. So we know that this is the number of protons, which means chlorine must have 17 protons and therefore 17 electrons, because it's a neutral atom, so it must have the same number of protons as electrons if it's a neutral atom. But then I've seen some of you doing some maths, which is great. If it's got a mass number of 35, mass number equals protons plus neutrons. So if we minus the number of protons away from the mass number, we're left with the number of neutrons, which in this case is 18. Really good. And what about this second one then? I think some of you have already done it, which is amazing. Anybody got any other ideas? What, or anybody else, sorry, want to have a go at working this one out? Again, we've got chlorine. We've got the atomic number of chlorine, so we know the number of protons must be 17, otherwise it wouldn't be a chlorine atom. Therefore, our electrons must be the same number because it's a neutral atom. So they've got to have the same number. And then again, we're going to need to do some quick maths. 37 minus, so the mass number, protons plus neutrons, minus the number of protons, leaves us with the number of neutrons, which, oops, I can't do maths, which is 20. Really good. Well done to those of you that have got that. And then just so that you're aware, we can discuss or describe our atoms as things like chlorine 35, chlorine 37, etc. But we can also talk about them using standard notation. And this standard notation can be a little bit confusing to remember. So you're going to need to kind of get it in your brain. But again, if you're just given two numbers, then look for the more massive number, because that is the mass number. But if you're given the standard notation, do you guys know which one, A or Z, is the mass number? Which one, A or Z, is the proton number? One of these is the mass number and one of these is the proton number, but which is which? Do you know which one is which? Evan's had a go. Yep. D as well. Good. Yep. So our A is our mass number. It is our mass number, and Z if you get a little bit more into science, or you take science a bit further, you start realizing that Z is used to kind of talk about charges or things with charges, and because protons tend to be charged, that is one of the reasons why it is linked there to Z, because our atomic number is talking about the number of protons, positively charged protons. So our atomic number is Z there. Let's just make sure that looks like a U. There we go. And then this central thing, which at the moment we've just called X, is just what describes our element. It's just the chemical symbol for our element. Yeah, Evan, exactly. Good spot, like mass spectrometry. Yeah. How do you know that already? That's ridiculous. So let's have a go then at doing the standard notation of chlorine 35. So if it's chlorine 35, we're going to put the mass number at the top. So we need to put 35 at the top. We know that chlorine has an atomic number of 17. So that's going at the bottom. So we've got our mass number. Oops. That doesn't say number, does it? That just says squiggle. Mass number. There we go. Is at the top in this case, so this is 35, and then our bottom number is our atomic number, which in this case is 17 when we're talking about an atom of chlorine. And then Cl is this symbol that you would find on the periodic table of chlorine. So let's do a bit of a test then, just see whether you've got this concept of an isotope. What is the same about an isotope versus atoms? Isotopes versus, isotopes versus other isotopes. What's the same then about isotopes versus other isotopes? If I've got, so for example, we could compare chlorine 35 and chlorine 37. Here we go. So what's the same about chlorine 35 and chlorine 37, and what is different? What's the same and what is different? Anybody got any ideas? Oh, Evan, you said your periodic table has it the other way around. Yeah, that's why I always talk about trying to identify which one's which, rather than just remembering that one's at the top and one's at the bottom, because in some cases they do write them differently, or they put the mass number only at the top, for example, or the atomic number only at the top of your little square with your element in. So that's why I try and encourage students to try and recognize which is which, rather than relying on remembering if it's top or bottom. Yeah, good. Okay, good. We've got some answers. Anybody else got any ideas? So let's look at the same first. What's the same? We know that the number of protons in isotopes have to be the same, because if it's an isotope of an element, it must have the same number of protons. And if it's got the same number of protons because they're all atoms, we're talking about atoms of different isotopes. So again, they're neutral, they're neutrally charged, so we must have the same number of protons as electrons. And if we've got the same number of protons, then we must have the same atomic number. So really good if you've got those. And then oppositely, it's not a word, but I'm going to say it anyway. Oppositely, the number of neutrons has to be different in isotopes, because that's the key point about isotopes. And therefore, our mass number of a different isotope must be different, because we're changing the number of protons in an atom. So if we're changing the number of, sorry, did I say protons? I meant neutrons. If I said protons, I meant neutrons. If we're changing the number of neutrons, we have to be changing the number of the mass number as well, because that tells us about the number of neutrons. Really good. Well done to those of you that got that. That is awesome. Okay, so now we're going to move on to using this new piece of knowledge that we've got. And one of the things we can use it with is calculating relative atomic mass. Does anybody know, and again, this is another definition you should learn so that you can recall it in an exam, what is the definition of a relative atomic mass? Or how would you describe, if you don't know a definition yet, how would you describe relative atomic mass? What does it mean? It's a bit of a wordy one, but there's a key word that we must remember for our exams in there. So anybody got any ideas what a definition of relative atomic mass is? Well done, Dee. You've got the key word in there. We have to have the word average or mean, which is really, really key. So well done. It is the average. And again, you can put mean if you want to put mean. This means the same thing, mean or average mass of an atom of an element. And if you're in A level, I've just seen you can compare it to an atom of carbon-12, so really good. I'm not sure what your name is, but that's for A level chemistry, you do need to include compared to an atom of carbon-12. At GCSE, we're quite happy to just say it's the average mass of an atom of an element, and it is compared, oops, because we talked about it being an average, it's because it considers, can't write today, considers all of the isotopes of an element. Because we know that there will be different isotopes, different atoms of the same element, but with different masses, we're taking an average of all of those masses. We're taking the mean of all of those masses. And this is why relative atomic mass, if you look on your periodic table, is often, not always, but often got some decimals. It's often not a whole number because it's an average mass of an atom of an element. Good, well done. Really nice, guys. So how is everybody feeling at the moment? Are we ready to move on and do some calculation, a couple more calculations? No worries, that's absolutely fine. If you want to join in, that's absolutely fine. We just want to double check that our GCSE students don't go remembering an extra complicated definition because they don't need to. So how's everyone feeling? 1, 2, 3. Are you feeling straightforward? All right. If you've only just joined us, you might be finding this a little bit harder, but please feel free to go back and watch our lesson from last week. Otherwise, if you're feeling really super confused, then please let me know because it lets us know how how you're finding it, how this is coming across, whether we need to do any more on it, spend any more time on it. But otherwise, looks like people are doing really well. That's awesome. Fantastic. Okay, let's keep going then. So there's another exam question. Again, this is Edexcel, but it's applicable to everybody, whatever exam board you are, you will be asked to do something like this, or could be asked, I should say, could be asked to do something like this. So they've told us the atomic number of boron is 5, and I'm going to highlight that. Boron exists as 2 isotopes, boron 10 and boron 11. Use this information to explain why boron 10 and boron 11 are isotopes. So it's asking, how do we know they are isotopes? So basically, what is the definition of an isotope? Okay, so whilst you guys are having a go at this, you coming up with an answer, it's 2 marks, so we're going to need to say at least 2 things, or give 2 points. Can you explain why boron 10 and boron 11 are isotopes? Got someone asking, how did you revise for GCSEs? There's some couple of really nice answers there. We can have a discussion about it at the end if you want as well, see if anybody's got any other examples, but I definitely agree. Questions. Obviously, you have to know content. And if you don't understand content, then spend the time learning content. But questions. Do lots of practice questions with friends, with teachers, with tutors. Just do lots of questions because it helps you to understand what you aren't sure about. So has anybody got an answer for this then? Lovely. Okay, lots of people, it seems, have got their head around it at the moment, which is really nice. This is basically asking, it's a weird way of asking, do you know what an isotope is and how can you prove it? So I think you guys have said, lovely, they must have the same boron 10 and boron 11. Oops, I need to put an and in there. And boron 11 must have the same number of protons. And how many protons do they have? Must have the same number of protons, but how many protons do they have? Oh, okay, no worries, Evans. Well, you can watch the rest of the class later, but you've been really involved, which is great because the more you put in, the more you get out. So really nice to have you. And we'll see you next time, hopefully. Thank you. Well done to those of you that have worked out a number of protons. Exactly right. It has to be 5 because our atomic number is 5. So really well done, guys. And why are they isotopes then? So I think some of you have also said that there are different numbers of neutrons. So in terms of boron 10, well done, D, you're straight in there. So boron 10 has 5 neutrons. It's doing the same bit of maths that we did before. And then boron 11 has 6. Oops, I didn't write neutrons in. Neutrons. There we go. And boron 11, sorry, has 6 neutrons. So that's the same bit of maths we did before. They've given us their mass numbers. So boron 10 has a mass number of 10. So mass number mass number minus atomic number. So 10 minus 5 gives us a number of neutrons, which is 5. And the same for boron 11, but it's 11 minus 5, which gives us 6 neutrons. Good question, Kelly. Can you write bullet points or do you have to write in sentences? So for an exam question like this, it doesn't specifically say that you will be given marks for your quality of written communication, or QWC is how it's written in a mark scheme. So that means you can write in bullet points. Now, if I were to just put a full stop on here and then put a capital letter there, actually all I've done is written in sentences. I just happen to have bullet pointed them so we can see that there are 2 different points there. So I wouldn't recommend writing in like shorthand or anything like that. But if you want to bullet point it out for yourself to make sure that you've got 2 marks or 3 marks, that's absolutely fine. If the question talks about having giving you a mark for quality of written communication or something along those lines, then you do get a mark for how it's written. So then I would definitely recommend no bullet points. But otherwise, bullet points are fine. As long as you're clear and they make sense, then that's fine. Good, lovely. So where are we now? Okay, next part of this question then. So a normal sample of chlorine contains only chlorine 35 and chlorine 37. Explain why the relative atomic mass of chlorine is 35.5. So this is basically saying, what is the relative atomic mass and how do we work it out? So what do we think, guys? What is the relative atomic mass and how do we work it out? Yeah, good, Zara, straight in there. It's an average. So relative atomic mass, oops, I have to rub that out now. Relative atomic mass is an average. It's an average of average mass of isotopes. And if it's an average mass of isotopes, why is it 35.5? Why is it closer to 35 than 37? That's going to be where our second mark comes from. Why is it closer to 35? It's 35.5 as an average mass, not 36. It's not slap bang in the middle. It's 35 rather than, or 35.5, sorry, rather than 37. So why is this? Nice, lovely. There must be a higher abundance or higher amount, you could say, of oops, need a H in there. Chlorine 35 than chlorine 37. Oh no, what's happened? Chlorine 35 rather than chlorine 37. Than chlorine 37. Good, really good, well done. Yeah, so abundance kind of means amount and that sort of thing. Lovely, so that's where you get your 2 marks from there. Okay, so calculating relative atomic mass then. So this is probably the hardest bit because it's a lot of maths, and it means you have to understand what you're calculating. So we're going to start, when we look at calculating relative atomic mass, by using just a kind of an everyday example, because I think that makes it easier to understand what it is you're doing. So let's have a look then at an example. So if you have 3 chocolate cakes of masses 136 grams, 137 grams, and 139 grams, what is the average mass of your chocolate cakes? I've got 3 chocolate cake in front of me, 136, 137, 139. What is the average mass of a chocolate cake, do we think? D, is the answer always going to be that 35 has a higher abundance? Like, for example, sometimes they give percentages. So you can look at what percentages they give, but in that case, we know that 35 must be the higher abundance because our average mass is closer to 35 than 37. So we know there's got to be more 35 masses of 35 contributing to the average mass, which is why it's bringing it down to 35. So what do we reckon? A, B, C, or D? What is the average mass of a chocolate cake? Oh, we've got a mixture. Good, well done, thank you, D. We've got a mixture of answers. So just to double check, we're looking at the average mass of a chocolate cake. So we're going to need to add them up. This is just a reminder on how to do averages or means. You have to add up your total masses because we're looking for the average mass, and then divide by the total number that we have. So we've got 3. So if we do 136 plus 137 plus 139 divided by 3, all divided by 3, we should get 137.3 grams. So it's actually none of these answers. So really well done if you said D. Yeah, good, exactly. Well done, Camilla. Lovely. So we've got, it's actually none of those answers because we do need to be specific about our averages. So that's really good. Well done. What about our next question then? Are we going to add in another chocolate cake with a mass of 136 to the collection? So what's going to happen to the average mass of a chocolate cake? If I'm including more chocolate cakes that are on the lower end of the spectrum or lower than my current average, what's going to happen to the average mass? Is it going to get higher? Is it going to get lower? Is it going to stay the same? Or is it none of these answers? Again, we've got a couple of different answers. So if my average mass was 137.3 and I'm adding 136 to my average, or including 136 in my average, it is going to bring my average down because 136 is lower than my average. So it's going to bring my average down. So the answer there is B. Okay. Right, I've realised I'm running slightly low on time, so I'm going to move forwards. So if we're looking, for example, then, let's relate it back to our chlorine atoms. If we've got 3 atoms of chlorine 35, 1 atom of chlorine 37, what's the average mass then of chlorine in this sample? If we've got 3 of chlorine 35 and 1 of chlorine 37, so it's the same as our chocolate cakes. Instead we've got of chocolate cakes, we've got 3 chlorines that weigh 35 and we've got 1 chlorine that weighs 37. What's our average mass of chlorine 35 then? Of chlorine, sorry, in total? So it has to be, it's exactly the same method. We're doing the average mass, so we need to add up the masses of each of our atoms. 35 plus 35 plus 37. And then there's 1, 2, 3, 4 atoms, so we divide by 4. So our answer should be 35.5 again. If we add up 35 plus 35 plus 35 plus 37, and then we divide it all by 4. Oops, I just moved my thing instead of drawing. We divide it all by 4. We should get an average mass of 35.5. Hopefully you guys got that. So when we're calculating our relative atomic mass, we have to calculate it using the mass number of our isotopes. And our abundance. So you'll notice that because I had 3 times as many chlorine 35s here as I did chlorine 37, I have to take account of that. So I have added up all of my chlorine 35s and then my single chlorine 37. So that is taking into account the abundance of the isotopes that are present. So just to finish this off then, calculating our relative atomic mass then, when we calculate a relative atomic mass, I think somebody put this already in the chat actually, when we're doing a calculation, we have to do our percentage or amount of whatever our isotope is. So I'm going to say A times by, the mass number, or the mass, but we're going to use the mass number of that isotope. And again, I'm just going to say A. You have to add it to the amount of B, or the percentage of B, times by the mass number of B. So again, B is just an isotope, and then we have to divide it. If we're using percentages, percent means per 100. So our total number of atoms there has to be 100. So it means we need to divide by 100. And this is where A and B are isotopes. And you could keep going. You can then add it to the percentage of C times the mass number of C, added to the percentage of D times the mass number of D, etc. And you can just keep going. This is just revision. Yeah, this is just a revision class going over stuff that hopefully you did at the beginning of the year, perhaps, or hopefully you did last year. We're just going over it. So super quick then, guys. Can anybody do calculate or write out the calculation that we need to use to calculate the relative atomic mass of chlorine? So in this case, we're using percentages. So 75% of chlorine atoms have a mass number of 35. All other chlorine atoms have a mass number of 37. So what percentage of chlorine atoms have a mass number of 37? 75% of them are chlorine 35. Chlorine, oops, that doesn't say chlorine. Chlorine 35. So what percentage is chlorine 37 then? I'm getting worse at writing chlorine. What percentage? Yeah, good. 25. Well done, those of you that worked that out, because it's 100% minus 75% gives us the rest has to be 25%. So the leftovers, all of the other chlorine atoms, is 25% is chlorine 37. So if we follow the calculation above, we've got 75% times by the mass number of chlorine, which is 35, added to 25% times the mass number, oops, in this case, which is 37. And then we have to divide it by 100 because we're looking at percentages. So our total number is 100. So divide it by 100. So our answer, again, should be 35.5. And you can double check because it should be what is on your periodic table. Yeah, good. Well done. Really good. Yep, brilliant. Fantastic. Lovely. Okay. We are going to have to finish now. So just to double check. We're not going to have time for this. So hopefully we have understood mass numbers, atomic numbers, and isotopes. And just so that you have had a chance, please check out our GCSE class schedule, because there are all of these classes available for you. So we've got physics, biology, maths, and chemistry on Monday, Tuesday, Wednesday, and Thursday. So please go and check those out. And don't forget to enter the competition. And I'll leave this screen up so that you guys, if you haven't already, you can have a look for your so you can have a go at inputting your email address, and then there will be 10 accounts to be given away, so you can win a free Snap Provides tutoring account for the rest of the academic year. Brilliant. So, well, thank you those of you that have hung around. Our YouTube live schedule is in the chat now, and so is the competition link, so you can have a go on that as well. This is just for GCSE. Yeah, this is for winning an account, a GCSE account, so that you would have access to all of our GCSE live classes, our all of the PDFs that go with those classes. You'd have an access to all of the previous classes we've done, and access to tutors to chat to. So A-level, I am not 100% sure what they're doing with A-level. You'd have to check out those classes, I'm afraid. But thank you again so much to those of you that have hung around. If you have any other questions, please ask. Otherwise, have a lovely rest of the day, and hopefully I'll see you next week. And if you're here, if you have only been here for a little while, please go back and watch our last video last week. There's another video there, and then you can watch this one as well. And hopefully I'll see you guys next week as well. So if you've got a question, please feel free to ask. I'll hang around for a minute and then we're going to disappear. So do you want to ask a quick question? Bye though, those of you that are disappearing, thank you very much. Well done. Hopefully see you next week. Did you have a question or not? Thank you. So I think my chat's being a bit slow, so I haven't received a question yet. Anybody? No? Okay. Perhaps you've changed your mind about a question. That's absolutely fine. We'll have a lovely rest of the day, guys, or rest of the evening even. And I will see you next week. Thank you very much. Brilliant. Bye. Well done, guys. Very well done.